Thanks everybody for coming along to today's talk. I know it's just before lunchtime, so hopefully nobody gets too angry and hangry with me. So my name is Maurice Gavin, and I'm the lead Android engineer at Toothpick. We build software for secure messaging between dentists and their patients. So security is something that's fundamental to everything we do. So today, I want to talk about why I think that any of our products could be hacked and how we can reduce the impact and mitigate that from happening. So in the talk, we're going to cover 3 different areas. We'll talk about the various different types of data that we can collect. We'll talk about how not to leak it as well. We'll look at the Android ecosystem and different products and tools that we can use to protect our data. And then finally, we'll look at how we can proactively identify problems in our apps before we release them onto the store. So there was a time that I thought I was too smart to be hacked. That notion was dispelled a few years ago when I logged into haveibeenpwned.com, and I found that all of these wonderful companies here had already leaked my credentials and my password publicly online. Not great, but it's better. Today I use a password manager and I use a different password for everything, so it's not too bad. But it is more critical in some domains. I don't really mind if someone finds my role-playing account, or if they take a €10 Uber on my credit card. But what does matter is if political elections are being subverted through the use of data. So, for example, Cambridge Analytica is a marketing and analytics company based out of the United Kingdom. And in 2018, there was a scandal that broke where it became apparent that they had been used to target and influence people online around the elections in the United States for Donald Trump and around the Vote Leave campaign for Brexit in the UK. There was so much concern and worry in the public mindset at this time that in Ireland, where I'm from, online advertising was banned for an upcoming election, and the government just said you just can't advertise online for any party or for any viewpoint. But then later on that year in May, the European Union brought in what is to date the world's most stringent privacy and data privacy policies. So these are new laws around consent, about how you should be informed about how your data will be used, penalties for the companies that don't obey those laws around consent, and guidelines for how to disclose if you do have a data breach. So the last example I want to give about the current state of affairs is in May of this year, WhatsApp, obviously a huge big messaging company with an enormous security team and really good product. They had a vulnerability that affected all of their users, both on Android and on iOS. So, I mean, if it can happen to somebody at the scale of WhatsApp, it can happen to any of us. So, what are some of the types of data that we can collect? So in our mobile apps, particularly in Toothpick, we really focus on health information. There are things like photos of your teeth and some information about how you eat and your medical history and so on. But this just is one type or one example of the data that we can collect. And we call it personal health information. You could also have financial information, things like what were your recent financial transactions. For example, I don't mind you knowing that my favorite color is blue, but I wouldn't want everyone to see my credit card history for the last 6 years. So it's clear that not all types of data are equally sensitive. We also have personally identifiable information, things like your name, your address, your date of birth. But these are all types of information that users give to us. There's also information that we generate ourselves, things like crash reports, device logs, analytics, and heat maps about how people use our products. And it's important to realize that these are types of data that can be lost, because this is often one of the sources of information leaking through mobile apps. So we all probably use crash reporting tools here. Maybe a show of hands who uses something like Crashlytics or Rollbar. Yeah, pretty much everybody, right? But one of the things you need to be careful about when you're using these tools is if you're logging network responses and all of the, say you've decrypted the data and you have all of that data in plain text, if there happens to be a device, like a crash on the device or the app crashes, all of that information could be in the device logs and shipped off to a third-party server. You might say that's not too bad, but what happens if Crashlytics or if Rollbar have a data breach on their database, on their backend? That information is then lost. Your user's information is then lost into the public, can be sold online, and worse again, you might not even know that it has been lost. Similarly with analytics, a lot of us have SDKs in our apps for generating information or harvesting information about how people use the apps, how many times they click on something, their user preferences and so on. So there was a very popular dating app that last year were found to have been sending all of the health information about their users to a third-party app that they were then using for marketing and messaging. I mean, it's not terrible because as far as we know, that data wasn't lost. But if it were lost, there could be huge implications for those users. They could have been denied health insurance. They could be stigmatized in society for their views and so on. So there are two golden rules. Only collect what we need, and you can't leak data that you don't have. So if you don't collect the data, if you don't have a reason to use it, maybe just don't collect it, because then you can't lose it. So moving on then, what can we do about improving the security of our Android apps? So I want to show you this castle that's here in Belarus. And the whole point behind a castle, of course, is that it is secure. So we've got nice high walls over here. Yeah, nice high walls and a gatehouse. So if I wanted to break into this castle, I'd either want a battering ram to knock down the gatehouse, or I'd want to be really good at climbing. So they're both great security features. Similarly, it's in a defensible position. It's got a river on one side and it's got a moat. So if I wanted to get to the walls, I'd need to be able to swim, or maybe I'd need to have a boat. So already it's becoming more complex to be able to break into this castle. I need to have different skill sets to get in. Similarly, we might have had some towers here at one point, and in those towers there might have been some guards. So not only do I need to be able to climb and swim, I also need to be able to do it quietly while not being spotted by guards. So the same principle holds true for our mobile apps. And this idea, or this principle, is called a layered security strategy. It's where you take many different types of data security and you combine them together to make it economically infeasible, or make it very expensive for an attacker to get into that app and to extract information from it. So let's look at some of the things that we can layer on top of each other to achieve this sort of strategy. The low-hanging fruit, obviously, is code obfuscation. If you're at the chat earlier on about shrinking apps, you'll have heard about R8, and I'm sure most of us are already familiar with R8 and ProGuard. Now, while ProGuard and R8 aren't security tools, their intention is actually just to shrink the app. It does have a nice side effect in that it renames a lot of the classes and methods. So you might have, encrypt file method, and that could be renamed to A or B or AAB. And obviously it's a lot more difficult to understand class names that don't make any sense and are just letters than it is to understand them if they're the full strings. So that's what ProGuard and R8 give us for free. They just shrink the code, and in doing so, they lose a lot of the context about the app. It makes it harder to reverse engineer. DexGuard, on the other hand, is an enterprise tool that is specifically designed for obfuscating your app. What it will do is it will take classes and it will take files, and it will encrypt them as you compile the app. And then at runtime, it will use keys that it has to decrypt them. Obviously, the weakness here is that if the keys have to be on the app to decrypt it at runtime, with enough time, an attacker could use those keys to reverse engineer it and still extract those files. So it's not perfect. It's not like a silver bullet, but it does make it significantly harder to get in. Another one I want to talk about is the network security configuration. This is not a very high-tech configuration file in the Android ecosystem, but it does give us a lot of control over what we want to do with traffic that we send across the network. So It allows us to do things like set up custom trust stores, override our settings for debug, say we want to use some local proxies and so on. We can set up certificate pinning. And these things were traditionally a little bit more tricky to configure, and they're very straightforward with the network security configuration, as we'll see in a minute. It's been around since Android N, and if you're unlucky enough to have to be supporting older versions, it is backported to 4.2 as well. So again, just a quick show of hands. Who here is familiar with what a certificate authority does? Okay, maybe about half or a little bit less than half. So we'll go through real quickly what a certificate authority is, because it's important to understand for the next step. So if you studied computer science or engineering, this is probably something that you read in a textbook at one stage and never really had to open up again unless you've been doing security work. But essentially, if we want to communicate from our Android app to, say, the MobileOptimized server and send a message, we assume that the channel that's sent across is not secure. So that becomes a problem if I have a sensitive letter or sensitive information that I want to send across that I don't want somebody else to read. There's a solution for this. So the MobileOptimized server can produce a public and a private key. The public key can be shared with anyone. So let's take that in our app. And we can use that public key to encrypt this message. So that message then can only be read by the private key. So we can now send that message across an insecure channel over to the MobileOptimized server. They can use their key to unpack it or to decrypt it and get back the original message. So that's how we can send information securely. But how do we get that public key onto the Android app? That's where the certificate authority comes in. The certificate authority publishes a certificate to say that this is the public key of the MobileOptimized conference. Because our devices come pre-installed with certificate authorities that we trust on them, we trust the certificate implicitly from the certificate authority. So the certificate authority will have certificates for many different organizations, not just the MobileOptimized server. And this forms the basis for trust on the internet. So mobile browsers, for example, will have a list of certificate authorities that they trust, and then as a result, they're able to trust individual servers that have registered with the certificate authority. So there is one downside to this. If, for example, our certificate authority is compromised by some sort of rogue or some sort of attacker, which has happened in the past, they can then publish fraudulent certificates and keys. So let's turn our certificate authority here into a rogue. The certificate authority obviously wants to replace these keys over here with its own keys and its own certificates. So this is now the key of the rogue certificate authority, and if our client fetches that and encrypts the traffic with that key and sends it across the network, it's intercepted by the rogue certificate authority. They can then decrypt that information, which is not what we want. So what we can do is we can use the network security configuration to specify these trusted routes. This is essentially just a list of certificate authorities that we want to trust. So if there is a certificate authority that has a history of being compromised, we wouldn't say add that to our list of trusted routes. Furthermore, the network security configuration file, it's really just an XML file. It allows you to set these different tags to configure the properties on across the whole app. You can do it for specific domains if you want. You can do it for debug builds if you want, and so on. So here's an example of it just being used for the toothpick domain. So anything we put inside these tags will only apply to the toothpick domain. So again, you can see just how easily configurable it is. This isn't really the interesting part. The interesting part is the concept behind it and why it's useful. And then similarly, we can set up our own certificates that we want to use just for our debug builds, which is often very helpful for test teams. So obviously, there's still a problem. What happens if there is a rogue certificate authority in our trusted CAs? Well, that's where certificate pinning comes in. Certificate pinning is where we just take the key directly from the MobileOptimized server. So say this is the MobileOptimized app for the MobileOptimized conference. We can just hand that from one team to the other, so we know we have the right key. And what we can do is we can bundle that inside the app, and we can produce a hash for it, and then use that hash in our network security configuration, so that only that key will ever be used to encrypt the traffic. This has its own problems. If they expire, you need to be able to update them, or else the app will stop working. So the network security configuration gives you a way of having backups to use if this one up here expires, say, today. So network security configuration, as I say, not hugely complex, but it gives you a lot of power with a very simple configuration. So if you want to learn more about it, there's some interesting links to follow. I'll put the slides up on Twitter afterwards, so if you want to check them out, you can do that. So I mentioned that if our certificates expire, that we need to replace them. And we don't really have a way of doing that. People can opt in or opt out of updates on Google Play. So it can be very useful, maybe not a great user experience, but it can be very useful to have a force update feature in our apps. So essentially, this is where if you find a critical vulnerability in a library that you use or somewhere in your app, that you can say to your users, look, you don't have to like it, but you do have to update to continue using this app. You'd often see this in banking applications and so on. If you use Google Play services, which I know not everybody does, but there is a new in-app updates library that makes it a lot easier to do this. So it gives us two ways of enforcing updates. One is optional, and then the other one is it's immediate. So you need to update the app before you can continue to use it. If you don't use Google Play services, or some of your customers don't have Google Play services installed, you can roll your own sort of in-app update thing where you have maybe a server that you query to check what the desired version is, and then you can have some sort of feature flag in your app where you can flick that on or off. So if the minimum version of the app is below the minimum version on the server, that you would show your own force update dialog. Force updates is not a thing you'll use every day. I think of it kind of like insurance. You hope to never use it, but if you do need to use it, at least it gives you a way to update your mobile app. So the next section I want to talk about is root detection. How do we know that the device we're running on is actually the device that it says it is? So there are two things to talk about here. The first is like traditional rooting with things like the exposed framework, where the system partition itself is modified. And it allows for things like API hooking and changing API calls on the fly. The recommended way to test for this and to do root detection is with the safety net API. Now, we'll see in a minute after we've talked through this why this has its own shortcomings, and we'll talk about other solutions. But there are some important takeaways, and some of the same principles apply across all root detection techniques. So let's jump straight into this. The compatibility test suite is a set of tests that are run by Android, or run by Google to check to see if an implementation of Android on some hardware actually works as intended, that it lines up to the APIs that are required. So people joke with me because I'm from Ireland, say, oh, you could run a computer on a potato. And I mean, maybe you could have some sort of weird Frankenstein potato where you attach your RAM and your processor and hook up a display. But it doesn't really matter. So long as it passes the Android compatibility test suite, you could have an Android run on a potato. So that's what we're really testing for here. We're testing that the potato, or that the device, passes the Android compatibility test suite. So how does that work? We first take let's take a situation here where I have a login call or maybe a payment call from my app to my backend. And I want to ensure that that call has not been tampered with and that the device hasn't been tampered with. So in a naive or traditional setting, you would literally just send the payment request across, HTTP request over to the API, and it would return a result and say, either that's good or that's no good. But we want to ensure that the amount hasn't been changed by some sort of rooted device or through some sort of API hooks. So what we'll do instead is we'll send over this initial request. The API will create a nonce. It's a single-use token, and it will store that in a table for looking up later, along with the metadata that we have sent up. That token then is sent back to the Android app, and then it uses the safety net API, which again also requires Google Play services. So you make a call to that API, you pass up the nonce, and then in the background, it will gather some more system information. It'll look for signs of routing, like a super folder or things like that. It'll harvest all that information, bring it up to the server. It'll package it all up in a JSON web token. It'll say whether or not it's a CTS profile match or whatever. And then it'll sign that with the private key from Google and return it back to the client. So at this point, you could say, well, we can just unpack that now, and we'll be able to see the information inside that as to whether or not it is a rooted device. And yes, you could. This contains the information about whether or not it's a rooted device. But if the Android app is a rooted device, it can simply just ignore that, or maybe it can just not call that method. So the last step here is that we need to take this web token, don't decrypt it, and send it all the way back to our server. So this JSON web token will be signed with the Google certificate, so we can check that that has not changed, that it hasn't been re-signed in some way, unpack it, and check to see that the nonce is the same as the one from earlier, that all of the metadata that we've passed up in our body has not changed, and that the device has not been rooted. So CTS profile match we've already talked about. That's sort of like, app hasn't been rooted, our device hasn't been rooted, it's not running on an emulator and all that sort of stuff. Whereas basic integrity is literally just saying, it's less secure. It's saying that you can have an unlocked bootloader, but that's fine. So if you want to use basic integrity, that's fine. But if you want more security, you use the CTS profile match. And then once all of that's done, and we've said that the device is not rooted, we can send it back to the Android app. And that's how we would do remote attestation with the safety net API. So if you want to learn more about that, then there's some more handy links. So as I said, that's not the whole story. In recent years, there's been a move in the industry towards what's called a systemless root. So a systemless root does not alter the system partition, and it's much harder to detect. So what it actually does is it modifies the boot partition. So if we want to be able to detect a systemless root, we need to be able to ensure that the boot partition has not changed. This is a little bit more difficult for an app to do, but there are ways to do it. So how does that work? Well, we need to use, oh sorry, I'm on the wrong slide. We need to use a trusted execution environment. So since Android 8, many Android devices that have been released have had this hardware chip on the device, which is essentially a secure environment for executing operations. So we can store things here like keys and so on that we can be confident haven't been modified. So the trusted execution environment it has its own key that it can then use to take like a fingerprint of the app that you are running, and it can sign it with that key and create like a certificate or a digest. You can then share that with your backend server, and the backend server can unpack that information and ensure that the key that has signed your app and that the app signature is the same as one that you've shared with it previously. This is pretty much what the safety net API does, not exactly, but it's sort of similar, only we've had to roll it ourselves. So we've had to build this ourselves. And it's a little bit more complex because obviously there's you have to gather the information yourself on the device, and then you also have to do the remote attestation. But if you're interested in learning more about it, a good place to start is this white paper, and it'll talk through how to use these TEEs and HSMs to generate these certificates and verify that the app hasn't been rooted. So we're almost finished with the improve your security part of the talk. But the last thing I want to talk about is multi-factor authentication. Unfortunately, this isn't something that we can do in isolation as mobile developers. Really, most of security is a team effort. But as our users become more tech literate, and I mean, dentists aren't the most tech literate people in the world, but they are aware of industry trends as they change. They are used to signing into their Gmail or their Facebook account and being given the option to be sent a text message to verify that, that they are who they say they are. So you have this idea of having something you know, like the username and passwords that I've had leaked all over the internet, but then having that backed up with something you have, like your mobile phone, which receives a text message or an RSA token. Or again, maybe you might use a biometric fingerprint to unlock your phone or Face ID, and that's something you are. So there are all these different types of authentication that are available to us today. I remember a couple of years ago, I was looking into security, maybe doing a PhD in the area, and this was very much a fledgling concept at the time. But it's really hit the mainstream. It's been widely adopted. It's baked into the ecosystem both for iOS and Android, and there's really no reason we shouldn't be offering these sorts of security to our users now. So there's some ideas that you can use to improve the security in your mobile apps. As I said, the best way to implement these is to layer them. Don't just pick one, pick all of them if you can, and it'll make it much harder for attackers to get in. So finally, let's talk about how can we identify the risks in our apps before they're exploited. Well, there's a few ways to do this. The first one I'll talk about is automated tools. So there are two main categories of automated tools. There's static analysis and there's dynamic analysis. Static analysis is where we have our code base, and we're able to run almost like a lint check across that code base and look for things like hard-coded passwords, insecure configurations, anything that's been sent in plain text, and that can all just be pulled out of the code base and flagged as a warning, and maybe you can fail your build on it. Tools for this are things like MobSF and so on. Dynamic analysis then is a little bit more complex. This is where you don't have access to the source code, but you do have access to the mobile app. So you can detect vulnerabilities at runtime. If you were trying to detect if say you were trying to attack an app that was using DexGuard, there's no point in doing static analysis on that because everything's already encrypted. Where you want to do your attack is at runtime, when those variables and when those methods and those classes have been decrypted, you want to try and hook in there to pull the information out at that point. And that's where dynamic analysis tools come in useful. Another one, and this is a static analysis tool I want to highlight, is dependency check. In the JavaScript and Ruby world, the prominence of supply chain attacks has really increased. This is where you're pulling in gems or pulling in libraries or you're pulling in SDKs into your software that you haven't built yourself. And maybe where that's being hosted on Maven has been compromised much in the same way as a rogue CA could be compromised. So you're pulling down software that you don't trust or you don't understand into your app. You can use dependency check to ensure that there are no known vulnerabilities, one with the app or with that version, and then you can also say, this is the specific version I want to use. You can take the hash of that version of the app, and you can put it into a configuration file. And if that hash ever changes when you pull down those dependencies again, so say the library has been replaced by a malicious one, it will throw a warning. So this is something that's good to be aware of. Certainly, as right now, supply chain attacks are becoming very, very popular. The beauty about any of these tools is that they can be automated. If you use any sort of continuous integration environment, you can just set these up once, and they will just continue to churn out reports, and they'll automatically notify you if any of these things crop up. So once it's a lot of effort to set it up, but once it's done, it gives you back the benefits for free. Obviously, the next best thing we can do to defend ourselves and our users is to educate ourselves. If you're just getting interested in security now, one of the best places to start is with the Android security documentation. If you're cross-platform dev or you're interested in both iOS and Android, or just security in general, the OWASP website is great, and they have a security testing guide that you can pull down yourself and use to audit your own application and find out where there might be deficiencies in what you've built. And then finally, the Android security team put out a great monthly bulletin. It comes out every month, and it's always worth a read. And then each March or April, usually, they will publish a security review about all of the attacks and CVEs and stuff that they published in the last 12 months. So again, that's worth some bedtime reading. The very last thing to do for identifying risks is maybe hire a penetration tester or bring in an auditor. If your app, if we accept that your app is going to be attacked in the wild, it's better that it's somebody that you have hired will do it and disclose that information to you, rather than somebody that you don't know. So they're my tips for how to identify risks. We're there at the end now, so let's just recap on what we've talked about. We talked about the various different types of data that we might collect and how to mitigate the risk of leaking that data through sanitizing your analytics and your logging. We talked about the importance of a layered security strategy and how it can be better than just having one type of security mechanism. We talked about how to encrypt your network connections and have a high degree of confidence in the servers that we're talking to. We talked about how to make it harder to reverse engineer the app through using obfuscation and root detection, and how to have that insurance policy of forced updates if we ever do need to put out an update. And then finally, we talked about how to identify the risks using automated tools, leveling up our own skill set, and finally, maybe hire a penetration tester if you're confident enough to stand behind your own product and you think it won't break. So that's the talk. If anyone has any questions, I guess I'll pull them off the Telegram channel now. So thanks very much for your attention.